with coherent change detection will show you exactly where the mower is at the time. The military is very, very hot to trot, as you can imagine, on this type of radar analysis that, again, the eye can't see, but the radar signal can see. A last example here on the radar wavelength, which many systems employ. Right now, C-band radar is a very popular one, used by European and Canadian sensors on the order of 6 centimeters. CSAT used 20 centimeter L-band radar. The Japanese are still using it to this day. And the Germans and Europeans tend to use the X-band radar, which is on the order of 3 centimeters. And all of them give you slightly different returns from the same surface. Here, a tidal flat on the North Sea. So all of these differences can be exploited to advance the interpretation. A few examples of SAR satellite capabilities that I want to explain to you in terms of how it's being used for R&D in coastal and marine regions. And there are a number of capabilities that I want to outline. I don't want to dwell too much on that. I have included at the very end of the presentation a list of quite good publications where you can dive into your heart's content and get sort of the long version of what I'm telling you this morning. Now, from CSAT evolving, we have much more flexible SAR antennas today that allow us to steer the radar signal either over broad areas at low resolution or to zoom into smaller areas at very, very high resolution. So very, very flexible systems that are in operation to date. The latest addition is the spotlight mode, where we can, moving along a flight path, steer the antenna in a way that we can illuminate targets of interest at very, very high resolution. Here's a list of satellites that have been in operation since CSAT in 1978, and you get the idea that radar is really a very popular system among space agencies, but not very well known. The various systems that have been flown came from Europe, from Canada, and from Japan. The Americans have done excellent work on the research and development side, but they haven't managed to put up a civilian radar satellite since 1978. Much of the work goes into the military side. Of course, there are some very, very capable radar satellites on the US military side. But let's look at some of the work that was done with civilian radar satellites in coastal regions. Here's an example of how surface winds, katabatic winds, manifest themselves on the ocean surface. You have this rather large plume taken in the morning hours of wind as it was flowing down from the mountains onto the surface of the ocean. Those are the kind of things that you can see with radar, as the roughness of the ocean surface is modified by wind activity. Here's another example of how radar can visualize bathymetry. And again, the main activity that is necessary in order for imaging that is how wind or modification of the wind and water surface changes as waves and tidal currents move over the bottom. Topography constrains the wave activity, which in turn gives you dark and light signatures on the radar images. And moving from the 1980s to nowadays, that's being exploited very heavily by very high resolution radars. Here's an example from Germany and the tidal flats along the North Sea. And again, those are exposed tidal flats that can be imaged very, very nicely in terms of the surface roughness by the German TerraSAR-X radar. Another example of research that has been done here in Canada, actually by D&D, involves ocean currents and frontal features that have been detected with SAR. Here are examples of the Gulf Stream area, sea surface temperatures from MODIS, chlorophyll concentration here in the image to the right, introduce the area that was outlined by the boxes. Here you have the sea surface temperature image of April 29, 2009, and the area that I will now introduce as a radar set image of that, the same area and the very same features that I've highlighted here, and that's what you get.
Dirk, 5 minutes?
5 minutes? Okay, I will move. And those features can be readily identified and automated in terms of identification on the images as well. Oil spill detection, we started quite early in 1996 with one of the first radar set experiments very close to home during the raising of the Irving Werle oil barge, and you can see the oil patches that had emerged quite nicely. We had to time that very well and managed to get it. Bilge, oil pollution by ships at sea, a very common thing here. Two examples from European satellites in Asia where the problem is systemic. Another thing that we have that I have mentioned is radar sensitivity to motion. Well, in this case, it's the motion of ships. You see the ships as very nice radar reflectors, but you also see the ship tracks here, and you see the ships displaced from their tracks, which is a very particular radar ability for motion detection, and you can actually determine from the measurement of the displacement the speed of the ship. Something that, you know, if you were closer would look like this. The detail that radar can see these days is quite enormous. Here's a half-meter resolution image of an oil tanker imaged by a European-Italian radar satellite. Here in Canada, we have concentrated much of our work on ice, sea ice, and here's an example of a mosaic of radar set images of the Hudson's Bay area. Much of that information, I will explain that later on, is used in an operational way for sea ice maps that are being distributed on an almost daily basis. For research on the other end of the world, here's an example of the Nimrod Glacier in Antarctica, and you can almost see the movement here, but you can determine that movement by interferometric radar and extend the measurements for the entire continent. And here is one of those examples of research that has been completed a couple of years ago by exploiting radar coverage of the entire continent in interferometric mode that gives you an idea of how fast the ice is moving and where it is moving. And of course, these measurements can be repeated so that you can get an idea, say on a decadal scale, how fast the glaciers are moving in that area. Not only on the land, but you can also get a pretty good idea by these weekly mosaics of how far the ice extends during the winter month in Antarctica. Much of that work is being done with synthetic aperture radar. The latest one is the European Sentinel radar, launched last year, and it provides some very nice images at C-band. Here, an example from the Azores, and if you zoom in, you can see here the wind action, slightly lighter in tone, and of course the wave action as well. Coastlines very well defined. It looks very clean here, but it is not always the case. The most exciting image that I found was this one. It's an island in the Bering Sea, and it has all kinds of very, very interesting and dynamic features in here that everybody will be challenged to analyze. There is open ocean and waves. There is ice in waves. There is ocean currents. There's ocean current modification by ice. Some lead areas. There is the island itself with the topography with katabatic winds coming down here. So there is a myriad of features that look very, very different from what you would see on an optical image that I've overlaid here from Landsat. Same area, but seen in the optical part of the spectrum, giving you a very, very different idea of the surface conditions and what you can interpret from radar. I think I want to conclude with that. I have a few more examples to show, but I want to encourage you to have a look at the presentation and other images as well, plus the publications that I've included in there. They are all on the internet at various levels of detail. They will give you sort of a short, a long version of this very short introduction to satellite radar. Thank you very much.
And one thing you didn't mention about the Sentinel is that that's going to be part of the open data thing in Europe, or we don't?
That's another talk. But since you mentioned that, the Sentinel data policy is very, very exciting. Similar to throwing the Landsat archives open in the United States, the Europeans have decided to make the data available freely. Which is wonderful, which is also a challenge for our Canadian colleagues here from the Space Agency and the Canadian government to perhaps encourage a similar policy for RadarSat, and specifically the RadarSat constellation, which is being planned for launch in 2018. Those are 3 satellites that sort of chase each other through Earth orbit and provide us with a deluge of radar information, which will be very, very useful. But, you know, can we all use it? And do we have the capacity, computational-wise, knowledge-wise, in order to do so? Perhaps the last message that I would like to leave you with is, you know, a single radar image, what is it good for? Sometimes it gives you a good example of what the potential is, but it really starts to scream when you manage to establish time series, to establish dynamics in the ocean, in the coastal area, and for that you need multiple data sets, half a dozen, 2 dozen or so, and you can't purchase a scene for $2,000, you know. Anyway, it would be wonderful if we can mimic that policy from the Americans and the Europeans for radar set. Thank you.